Most of this is a review, so I'd ask you to read it on your own. I'm just going to go over some of the highlights. One of the things that you absolutely need to know is what a proton is. If we have a hydrogen atom, it has one proton and it has one electron. If we remove the electron, we are left with a hydrogen ion, a ion that is positively charged. If this proton is in water, and all acid-base chemistry is performed in water, it makes something called a hydronium ion. You can see the water and the proton reflected in the hydronium ion. Okay, some things for you to read. Here's a term I would like you to know. A binary acid contains two types of atoms. So hydrochloric acid is binary. There's a hydrogen and a chlorine. Hydrosulfuric acid is binary also. It only has two types of atoms. A ternary acid is a proton bonded to a polyatomic ion. So this is a ternary acid. This is a ternary acid. A carboxyl acid has a COOH group in it. I'm sure you've heard of citric acid. That brings us to the way to describe acids and bases. An Arrhenius acid is one that produces hydrogen ions in water. Here is a classic Arrhenius acid. When hydrochloric acid is in water, when hydrogen chloride makes hydrochloric acid in water, it breaks apart totally into a hydrogen ion and a chlorine ion. Here is a base. Sodium hydroxide in water breaks apart or ionizes completely into a sodium ion and a hydroxide ion. The Arrhenius model did not work well when we discovered weak bases, so instead we describe acids and bases in terms of the Bronsted-Lowry model. An acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. You're looking for a non-bonding pair of electrons to accept the hydrogen ion when you're talking about a base. If in a Bronsted-Lowry equation you are given um, the acid and the base, and you look for what happens to them on the other side of the arrow. So here we have HA, which would be the proton and an anion, and we try to find what it looks like on the other side of the arrow, and we can, and we see the difference is it has turned into an anion. What is missing? The proton. The proton has been lost. It has been donated. So this is the Bronsted-Lowry acid. This is called the conjugate base. If we look at water, which is the Bronsted-Lowry base in this equation, and look at it on the other side of the arrow, we see that it looks like this. It has accepted a hydrogen ion concentration, a hydrogen ion, so it is, this must be a plus, so it is a Bronsted-Lowry base, and its remnant on the other side of the arrow is called a conjugate acid. Please note that these two things occur in tandem. The acid is donating and the base is receiving. So we're only talking about the acid and base as a reactant, and the conjugates would be the products. So here we have a Bronsted-Lowry base and an acid and the conjugate and acid and the conjugate base. How can you tell? You have to look at the other side. So a particle diagram, the unbonded electrons make this the base. the water gives off one of its hydrogen ions, and it becomes NH4 and OH. Okay. I did not talk about the charges. If in Bronsted-Lowry acid equations you leave off the charge, you are not correct. So let's look at this equation now, and we're going to look at the reactants, see what happened to them as the products to define what they are. Well, HBr as a reactant is Br minus as a product, so we know it has lost its hydrogen ion, therefore it must be an acid. The NH3 ammonia has suddenly acquired an H+, so this must be the base. And so the base on the other side of the arrow has a conjugate acid. The acid on the other side of the arrow is a conjugate base. What is the conjugate base of H2S? Well, if it is a conjugate base on the other side, that means it's an acid on this side, so the conjugate base must show us that it has lost a hydrogen ion, so that would be correct. And this says what is the conjugate acid of NO3 minus 1, so this must be the conjugate acid, which means this acts as a base. So we are going to look at a hydrogen ion that has been, hydrogen ion has been added. So the H is added, and the H plus would neutralize this negative, so there we go. Okay, an amphoteric substance can act as either an acid or base because they can transfer an H, and they also so they can lose an H and they can take an H plus because they have a lone pair of electrons. Water is the big amphoteric one that you should remember. Okay, now this is a common misconception. When I'm talking about strong versus weak, I am not talking about concentrated versus dilute. Concentration and versus dilute is when you talk about molarity. That is not what I'm talking about here. Strong versus weak is the ability of the acid or the base to dissociate completely, to break apart. So here we have a strong acid. When a strong acid is in water, it breaks apart completely. 100% of all the HCl particles will break apart into their ions. Remember that an H plus and H3O plus, the hydronium ion, are interchangeable terms. Okay. A strong acid or a strong base is a strong electrolyte because there's a charge. And there are a lot of charges because all of the particles break apart. A weak acid is a weak electrolyte because only a small percentage of the particles break apart. All right. So a weak acid is one that does not completely break down. What happens? An equilibrium situation happens. And some particles form their ions and some stay as the molecules. So a strong acid has weak attraction between the hydrogen ion and the anion, more attraction for the hydrogen ion to water than for its anion. So it completely ionizes, completely breaks apart. We would use a single-headed arrow to denote the ionization of a strong acid. A weak acid, such as acetic acid, has a few hydrogen ions formed and then a few acetate ions formed, but the majority of the acid stays in this molecular form. The hydrogen ion has a stronger attraction for the acetate ion, keeping them together, than the hydrogen ion has for water. Okay, you can talk about bases in terms of their ionizing ability. A strong base completely breaks apart, completely dissociates. A weak base does not. And I have given you a bunch of weak bases and show you their ionization um, reaction. When we're talking about weak bases, you need to make sure that you put in the water when you're talking about them ionizing, because it's a little difficult to follow otherwise. Remember, it's acting as a base. The water is acting as the acid, and what happens when it dissociates in an equilibrium situation can be best seen this way. It's a lot easier and less confusing if you talk about it with adding the water. One more thing that appeared on the AP exam very recently, you were asked to tell the strength of a group of acids just by inspection. So let's look at these ternary acids, and I am writing them in from strong for chloric acid to weak. Okay, so when you look at this, these are called oxyacids, as you recall. The more oxygens they have, the stronger they are. I'm going to look at phosphoric acid, which is a weak acid, and then I'm going to look at some other acids. Remember, these are all acids because they have the ability to donate a proton, I guess, except for that one, so we won't talk about it. The more H's they have, the stronger the acid.